So it's a beautiful day here in Canberra, and we had a light mist early on, and then the sun cut through it and kind of warmed the ground, and I thought, wow, what a beautiful scene. You know, the frost was melting, and then I thought of, you know, the kind of countless times that process must have happened, and the kind of unnumbered generations of people who have walked this land through thousands of years, countless thousands of years, and how this land created them, and they contributed to creating that land. So that's kind of my mystical experience for the morning. But I'd like to acknowledge the traditional owners and custodians of the land that we're on here, this beautiful land around Canberra, which is the home of the Ngunnawal, Ngambri and Aurigo people. And I'd like to pay our respects to their elders past and present, and also extend that respect to any Indigenous people who are joining us for this presentation. So in terms of housekeeping, I'd say first thing is don't panic. If you can't access the SharePoint drive or the OneDrive that was sent in the information, don't worry, you don't need it at the moment. You will need it for the next week's workshop when we actually get into running our own things. The problem here is that the ANU, having been hacked so many times by various people, is now very hyper secure. So Larissa has to add your email.
Yeah, but I just managed to do it, Simon. I put in, oh, so I sent only to Atum, sorry, I sent to everyone here.
Okay, so we can now hopefully all access the SharePoint files.
Yeah.
But you won't need them immediately. And if you do have problems still, please post that in the chat. The workshop's being recorded, and that's because a lot of people who couldn't be with us today would really like to have access to those recordings. So just so you know that this is being recorded, and you'll be advised later on when the recordings go up on the Mercury Australia website. And please feel free to ask questions during the presentation. It's going to be fairly informal, so don't feel like you have to wait until you're asked to ask a question. Or you can post them in the chat if you feel that, you know, it's something that's not particularly urgent or pressing. And we'll do our best to get around to those. All right, so I think Larissa now will introduce Marco, and I'll stop sharing.
Thank you so much, Simon. So as Simon said, yeah, the OneDrive from the ANU is quite secure, and even though now some people could access the folder, there might be some people that won't be able to, because sometimes there are problems between institutions, so to recognize emails. So yeah, just let us know in case that happens. And yes, so I also want to, before I introduce Marco, I'd like to thank Simon and Kelsey so much for their help, especially Simon with his organization skills. I have to say that this workshop is all organized and built by Simon. He put a great effort and had great ideas for the workshop, and Kelsey also for feedback, like backing us up during the workshop. I don't know if everyone knows, but I have a baby here, so I won't be in the workshop all the time. So thank you so much, Kelsey and Simon, for helping. So before I introduce Marco, I want to say that I had the pleasure to meet Marco in a bacon workshop in Mexico. And so we became friends, and we actually published a paper together. So maybe from this workshop, there'll be other people publishing papers with Marco as well. And so we became friends, and some people saw this paper published with rPlum, and they approached me, oh, you know, I'd like to talk about rPlum. I was like, maybe Mark should run a workshop for us here in Australia. And that's how this workshop came up. And so I really would like to thank Marco for willing to spend time with us and teach us about rPlum. We are really thankful about it. And so Dr. Marco Aquino Lopes, he did his master's degree on probability and statistics at CIMAT, which is the Center of Mathematics in Mexico, where he is doing a postdoc now. So he was supervised by Professor Andreas Christen, and I think you have seen Andreas Christen name on Bacon, the other package that is for age depth modeling. So he was working on the F14 carbon on radiocarbon dating, asking the question of whether it's possible to go directly from F14C results to calibrated dates. And then for his PhD, he moved to Belfast. And so he was working with Professor Martin Blau on age depth modeling, where he developed the mathematics and beta versions of Plum, which we're going to learn today. So he's currently a postdoc at the CIMAT, and he's developing rPlum to include reservoir effects and improve the mathematical structure in the modeling. So I'd like to hand this to Marco. Thank you so much, Marco, for being here with us, especially because it's nighttime in Mexico. Thank you for fitting us with our time zone.
Oh, thank you for inviting me. This is a very nice opportunity to engage with people from across the planet. So this is great. And I'm glad there's some interest in the model. So I think the best way to start is to just start introducing, I don't know if I have sharing privileges. Yes, give me a second. There you go. I'm going to start by talking a little bit about the model, what is actually, what Plum is all about, basically. I'll try to go into a little bit of the details. Don't worry if you guys get lost. It will all make sense later on. But in this, the point of this part of the talk is to introduce some of the restrictions, some of the assumptions that we're using in the model, and then how should we properly use the model, not just the package, but the actual mathematical model. So when it is appropriate to be used and things like this, for example. So let's begin to ask the question, what is Plum? So Plum is a Bayesian methodology for age-depth modeling of lead-210. So the first part, a Bayesian methodology, I'm pretty sure many of you will be familiar with Bacon, where Dr. Blau always talks about the Bayesian methodology and how we use prior distributions and then data together in order to get a much better chronology, and then that we use millions of simulations in order to get a much better estimate of the age-depth model. So Plum is based on the same idea. So we have some prior distributions that I'll go into detail later. So we have some prior knowledge before you go and take your core, before you go and select your site. From all the experience you got, you already know, for example, if I go to this lake around this time, around this depth, is going to be around this accumulation rate. And I heard this from many researchers, like even before going and coring, you guys already know roughly an estimate of how that lake or peatland or ocean is going to behave. So Plum and Bacon use this information as a starting point. This is what we call prior distributions and prior information. I'm going to stop a little bit here just to mention this. Many scientists sometimes don't agree with the Bayesian methodology because they say we're contaminating the results with prior distributions and that it should be like a blank slate. The philosophy here is completely different, isn't it? The point here is to have a learning process. So you guys have a good idea of the sedimentation rates, for example, or how it's behaving in your lake. But you will not know the details until you take the core and measure it, right? So the idea behind a Bayesian methodology is that, so you may have a good estimate before doing anything, but then that estimate gets refined and gets much better with the data. And what happens if your data is not agreeing with your prior information? Well, that is great, because then your prior information or your current knowledge gets modified and gets updated, right? There's a lot of talk about artificial intelligence and how models get updated and all of this. The idea is very similar. So as you put more data into these methodologies, the results gets much better. So sometimes you will have a core that doesn't work very well with the default settings of Plum or Bacon. You start changing this a little bit, and then you'll get much better results. We'll see that a little bit later. Now, what is the main difference between Plum and the traditional led to 10 dating methods? Well, I would say the most important difference is that we separate the age-depth part of the methodology from the decay relationship. I'll show later, a little bit later, the equations for the CRS model, or the constant rate of supply model, also known as the constant flux model. But I'll show you there that the age-depth relationship and the decay equation are one, and that I'll demonstrate later that becomes problematic. We separated these two phenomena because they're completely different phenomena. They work together, but they're different, and we separated them into two different equations or models, and then unite them using the Bayesian methodology. So that's the most important part of the model. And because we're doing this separation, we are able to use other dating methodologies to improve the dating or the age-depth model. So, for example, if you use the CRS model and then you have a cesium date, what most people do, and what is actually recommended, and I would also say you should do that when using the traditional models, is you run your CRS model, and then you check if your CRS model agrees with your cesium or your other independent dating. And if it doesn't, then there's many trickeries there to kind of force the method to go through the cesium, right? This becomes a problem because then the cesium is no longer useful for validation because you're forcing the model to go through there. And then the other problem is you only have one point or one dating to actually fix your chronology, and then you have to manipulate what's the name of this? I forgot the name. When you sum all the activities, the inventory. So you have to start modifying your inventory in order to make that work. So this is actually a little bit more subjective. The user has to actually go into the data and manipulate it in order to agree with a point. So because we're using a Bayesian methodology, you incorporate this information into the method, and then you no longer have to manipulate your data to agree with the method. You just tell the method, this is an extra point, this is more information, and the method will take it into consideration. And if it agrees with the method, the dating agrees with the lead, it would become a much better dating. And if it doesn't, then it will doubt, and you will see bigger uncertainties because it's not agreeing completely. So it's not the user who is forcing the model, it's actually the model deciding what is best for it. So let's see a little bit of the CRS model, which is the most traditional. Give me a second. So I don't have to go into much detail about this. You guys know about this. You go and take a core, you have your surface, and then you have your deepest part, right? So when you go and do this and then decided to use the CRS model for dating, one of the things you need to assume is that you reach background. So in the equations, you have to say, oh, I reach a point where there's no longer external lead to 10 coming into my data. So that's why I put here an infinite and a question mark. So you have to assume you reach far enough, right? So this equation right here comes from the actual decay equation. That's the decay equation is always an exponential equation. So when Appleby and Oldfield got the idea of this magnificent model, they kind of clear out the time part of the equation and then got this equation. So at the time it was fantastic because there was a way to actually get time if you have the complete inventory and then the inventory up to a certain point. So this is great if you actually take your core and measure the whole thing. You just have enough samples and just continually sample everything. This is actually very good when you have that situation. If you core the whole thing, you measure the whole thing, this model will give you fantastic results. I'll show some comparisons later on and that I did with some simulations, and it is actually very, very amazing. It has one of the big problems here, even when in the best scenarios. What happens here? This is the remaining, let me see if I have some sort of pencil here. What happens here? This little guy here is the remaining activity. Sadly, the remaining activity, as you get closer to infinity, as you go deeper, it becomes smaller. So what happens if you have a smaller number going to 0 here? This whole thing will go to infinity, right? So what does that mean for us? What does that mean in the actual core? That actually means that after a certain threshold, you will see an artificial increase of the accumulation rate that is not reflective of your actual core. It's just the mathematics, the way they were done. So if you get close enough to that 0, you're gonna make this go to infinity, and that will just become crazy. And this is amazing because if you go to many papers and you see a CRS dating, you will see something like this always, this little part. Martin and I like to call that the tail or the trumpet, because it kind of just goes to infinity. And there are many papers discussing this, and they actually say, well, you need to cut it. You need to remove it from your dating, which I agree. It needs to be removed because it's an artificial increase on the accumulation rate. It's not real. So this is where you need to be careful. Now the question becomes, when do you cut it? At what depth do you cut it? What accumulation? So that becomes a much harder question. And I mean, there's experts on this model that would be able to answer that question, but to be honest, I don't know. I just know that phenomena exist. And when I started doing my PhD, I remember Martin gave me the assignment to say, well, try to incorporate lead to 10 into bacon. And when I started looking at these artificial increases, I was like, this becomes a problem because there's an artificial increase in the accumulation rate. And all the little samples are not independent from each other. They're actually dependent. If I put them directly into bacon, that's gonna violate all the assumptions we make in bacon, because in bacon, we assume that the dating is precise and we assume that all of them are independent. So when you guys put the series method into bacon, you need to be extra careful because the series method doesn't give you independent datings, and bacon will think they're independent. So you're gonna make the bacon model believe he has more information that he actually has. And sometimes it becomes a problem because it will listen more to the lead to 10 part, because of course there's a lot more samples in it than the radiocarbon, because your radiocarbon are way more expensive. You guys have way less radiocarbon dates, but a lot of more points of lead. But again, those are not independent dates. So Bacon doesn't know how to distinguish that. So the model is great, but we need to be very careful when we use it, and even more when we use it with Bacon. Okay, when you use it independently, the uncertainties might be, I'm going to show later on that they're actually quite small, but sometimes they're sufficient if you guys took enough information from the core. Okay, let me see. How do we stop this? Here we go. There you go. So what do we do in Plum instead? So we're not thinking of remaining accumulation. We're not thinking of taking the whole thing. What we say is, it's quite simple. We have a sample, you guys go take your core and then cut some section, a slice. So that slice that you guys take, that's our measure or measurement, that's our data. So we have some depth X and then some depth minus a thickness of your sample, which is this little sample right here, right? Well, that sample right there has some supported activity and some unsupported activity, and then some uncertainty that the labs gives you, right? This is a measurement from a lab, so we might be safe assuming normality. So what Plum does is saying, I don't know anything about here or here or here. I only know these two measurements, but I know that there exists some level of supported activity and some level of unsupported activity. And that's all I know, right? And then we assume it normally distributed.
Sorry, Marco, when you say you assume it's normally distributed, in what way do you mean? That the errors are normally distributed?
Yeah, but not from the dating, the actual measurement of lead.
Ah,
So,
okay. Yeah.
so when you, this is a good question. So let me show you really quickly here. Let's see some data really quickly. So this is our default core. So when you work with Plum, you're gonna use your raw, what's going on? You're gonna be using your actual raw data of lead to 10. Oh, I can't open it for some reason. Give me a second. My computer is acting up. Give me a second. There you go. That should work. I mean, this is just, I'm not text editor, but we should be able to see the data. Okay, let me continue. I'll see what happens later. So when you know, technical difficulties all the time. So when you actually measure the lead in a sample, we can sort of assume that's normally distributed, right? So not the measurement, not the dating, not anything like that. So the actual measurement from the machine, that would be normally distributed. And I have some doubts that it's completely normal, but normality has actually worked up to now. We're actually thinking of changing the model to be a T distribution, just like we do with radiocarbon.
Yeah.
But we need to do more tests. So if somebody can show me that the lead to 10 measurements are not normal, then I could actually, that would be really good, because I could actually think of a better distribution for it. But for now, this is the way it works. So by using sort of the same equations that Appleby and Oldfield came out with, and actually Robinson's as well, came out with, I can actually, instead of solving for the T, which is what Appleby and Oldfield did, I just decided to, here. I just decided to leave it in, but solve the whole thing and solve it for this interval. So instead of going the integral from infinity to x. I'm going the integral of xi to xi minus delta. Solving that same integral, I come out with, we didn't have machine power. The problem will be, well, you have a t here and a t here, and that becomes a big problem. But now we have computer power and we don't have to worry about that. We actually say, well, that t is one of the parameters of interest. But that t is not just a t, it's not a value. It's actually a whole system, right? So this t is actually a relationship between depth and time. And as models like Bacon or bCrum or Oxcal have shown us, is that these things have a whole new, a whole system itself. Regardless of the actual decay of the isotope, the actual process of accumulation is a whole phenomenon itself. So at this point, I could actually use any sort of t function. I could actually say, well, I want a line. I actually want some curvy thing. I could actually go for the same process as Oxcal, or I could actually go for the same process as bCrum. But, well, I work with Martin and Andres, so we say, well, Bacon. So that Bacon, what we actually call Bacon is the process of that function that goes from depth to time. And that's what we use in here. So in order to solve these equations in the machine, we gave the machine Bacon for it to solve these equations. And now we have other parameters such as the influx of lead that is coming into the ground. So one of the things that Plum has is that we could assume that the influx would be different at each step, but then it becomes too many parameters and it becomes too unstable. So for computer reasons, computer power reasons, we assume this to be constant throughout the core, which is a very similar assumption as to the CRS model. Now, this could be corrected later on, but it requires a much different model, an actual model from this parameter. So in order to don't do that right now, and most cores don't actually need that. So that's why we decided to keep it constant for now. But it could be changed.
So Marco, can you explain to people like me who are not very mathematically savvy what the difference between the CRS and this constant flux assumption is in terms of what it means for the dates?
It actually, the assumption that, okay, one thing is the assumption and the other one is the model.
Okay.
So this, yeah. So the assumption pretty much says there's a constant flux of lead coming down to the ground, right? That's the assumption we're using in Plum and in the CRS. So there's just a constant flux of that. But just the CRS became so popular that it just got the name of the assumption to say so. The model is actually where is it? Here, mouse. So this equation is the CRS model, but the assumption is the assumption that throughout time lead has fallen at a somewhat constant rate. Right? So we're using the assumption, but we're not using the model.
Yep.
Right?
Yep, that makes sense.
Yeah, well, we're using right now we're using for computer reasons, as I said, for computer reasons throughout the whole core, but the assumption is localized, right? So
for each section of the core.
Yeah, mathematically speaking, we're assuming that there's a constant flux within this sample.
Mm. Yep.
Much shorter time.
But not through the whole core.
For now, as it is the model right now, yes. But we're working on actually changing this, because we feel for other, not that many cores, but a good portion of the cores, that assumption is broken. I mean, permafrost, for example, is one of the things that we're in big discussion if we can assume a constant flux or not, because yes, there is constant flux, but someone gets trapped on the ice, and there's a whole new process and all of this. So that's why we're working on actually easing that assumption, but that's actually future work. So mathematically speaking, this is actually the model. So the model is, we have now a model with a lot more parameters, which is the flux and the time relationship. And that time relationship, it's a Bacon time relationship. So if any one of you have seen the original Bacon paper, this is the equation behind Bacon. So we have accumulations, and then we have a parameter of memory. So I'm pretty sure people have always questioned what that memory is. And it's actually, it's no more than just a parameter that tells the core how flexible it should be on regards of if it should become very curvy really quickly, or it should try to stick as a line. So, and many cores require different parameters of this, and that's normal. Let me see if I can get the animation working here. I should be able to. Yes. Give me a second. Martin does a great job doing these animations. I always kind of use them. So this is not exactly what Bacon does, but it's very similar. So it's creating little chronologies every iteration, and we do this millions of times. And it is checking if each of those iterations follows the assumptions we're giving the model. So in this case, he's asking the question if they are all ordered, and he's keeping only the ones that are ordered. In our case, it's a much more complicated, and it is a model where it follows all of these equations. But the idea is the same. We're creating a model from millions and millions and millions of tries, right? That's what we call, yes.
Oh, so Marco, so the animation showing that the age depth models in green are accepted because all of the dates go in chronological order, but the red ones are not accepted because they have age inversions. Is that right?
Yes, that is the assumption this model is creating.
Yeah.
All models are much more complex, so it is quite difficult to show you in an animation like this, but I'll try to do that later on. But the process is the same. We're creating millions and millions of iterations, and some of them get accepted and some of them get completely rejected because either they fail on the assumptions, they fail on something, and they are useless. So we're running these millions of times. So that's why I like to compare this sometimes to artificial intelligence, because we're doing millions and millions of iterations just to get a couple of good ones.
Can I ask a question? Sorry.
Sure.
Gabriel here. I was just wondering, those blue curves that you had where you were getting the dots in that animation, the little blue curves, are they the distribution of that you assume for each point, or?
This was done for radiocarbon dating. So these are radiocarbon dates, calibrated radiocarbon dates.
And so you get a distribution for those dates? Is that...
Yeah, so what you get when you calibrate a date is actually a posterior distribution. The actual process of calibrating a date, a radiocarbon date, it's almost like you get a posterior distribution. So you get these curves that are not symmetrical. So what happens here is he puts them at certain depths where he took the samples, He
Yeah.
calibrates them and then just runs lines through them
Yeah.
and just which lines actually come up with a reasonable model, which is that they're in a chronological order. And then he keeps that one. So that's why it gets in great scale.
Sure. And I
And then-
guess it'll do that with, I guess, the more probability depending on how probable that point is. Is that what it does as well, or does it just randomly? Yeah.
So if you've seen Bacon models, sometimes you see darker areas, right?
I
don't know if
haven't
you-
worked with Bacon models. It's my first time doing this, so sorry. I'm trying to understand.
For people who have seen radiocarbon dating and Bacon working on this, you will see darker areas. And those darker areas are places where there's more probability for the dating to be there, right? So the same idea is here. And you're correct. Darker areas or places that are more frequent are more likely and they're therefore more probable, and the probability there is higher. So yeah, so we're basically doing this sort of experiments millions of times just to get a probability.
Great, thanks.
You're welcome. Perfect. So let me continue the talk. There we go. Oh, there you go. So this becomes then very difficult, but this is just a mathematical artifact to reflect the model. We assume normality, and that's their normality right there. And then we have that model I show you there. This is the Bacon model in H. And this is the influx of lead to that section, and then the supported activity. Now, the CRS model and any model out there removes this manually. So they never work with supported activity, which is the local lead to 10. So it's always calculated before doing any of the models. For Plum, we don't do that because we want to reduce user inputs as much as possible. And supported activity is one of those things that is critical. If you move that by a little bit, your dating will be very different. So it's one of those parameters that is very delicate and you need an expert to actually do that. But because Plum it was taught for people who are not experts on that field, we decided to keep it there and let the model decide what's the best supported activity for that model. So this is actually quite good because you can go directly from the machine to Plum and then to get a dating. By solving this equation for all the data, then we get the likelihood, which is something like this. This thing up here is just the sum of all the data. You don't have to worry, but the important part is this part down here. This one, it's saying there is a supported activity, and then we have data for that supported activity. So we keep we keep the parameter for the supported activity, but we need to give the model some data that comes from the supported activity. Okay, so yes, you're not calculating it yourself, but you need to give the model some data for it. So you will need your lead and your total lead, and then some sort of supported measurements, supported lead to 10 measurement, which could be the 2,6 iridium or just the tail of your lead to 10 if you reach background. So that's if you have some proxy or some way of calculating the support activity, sometimes you don't actually need to reach background, but if you don't have that, you actually still need to reach background. So this is really important. You do need some sort of way to guess your initial supported. And then prior distributions, again, or prior knowledge of these parameters. So the supported activity, we left it as somewhere roughly between 20 becquerels per kilogram. which is something I saw in many courses that I was analyzing in my time doing my PhD. That hasn't changed. I mean, if you guys have a site that you know very well what the support activity is, then you change that parameter right here. So it is a gamma distribution, which looks something like, looks something like that. It starts at 0, goes like that, and goes like that. Your mean will be somewhere right there. For the default values of Plum, that'll be around 20. For the influx, again, that's depending on your site. This one is an estimate from a paper by Appleby that estimated that the global influx of lead was about 50 becquerels per year, per meter per year. To be honest, I don't believe that. I do suggest that if you have a much better estimate for that, by say from prior studies done in the area or something, you do change that. But Plum is very well behaved, and it actually, even though this is a very bad prior, it gets fixed really quickly, and I'll show you that later. The accumulation rate, we are estimating a mean of 10 becquerels, 10 centimeters per year. Sorry, 10 years per centimeter. And then the memory is roughly in the middle. So we're not favoring either strict models or very flexible ones. We just let the model do what he thinks is best. I'll try to explain this a little bit better when I show you some graphs, because this is actually quite important later on, and it's usually overlooked. But if you guys have some question right here, you're free to ask me. So this is actually what Plum looks like. Again, if you've seen Bacon, you'll be familiar with this style of graphing. You see this plot right here. Everybody asks me, what's that? Well, that's just to check if the model work. We call it converge, but it's actually just to check if your model is actually worked, right? So right here, you just see noise. There's not a clear structure. If you will see something like coming up right here very clearly, and then down here, and then moves again, or something like that, if you see steps, that model did not converge. You need to run it again, right? If you see some pattern, for example, going right here, going down, or going up, that's actually, again, bad. That means, again, that the model is not converging. We're doing it, again, we're doing all of this by a lot of math of tries and errors that the machine is doing millions of times. And even though we can let it run for twice the time, it could still take some time to converge. So this plot is there to check that the method converge. So many people just go and erase all of this. I always tell them, don't do that, because this is all the information that your HDEV model actually work and is valid. Because if you try to publish something with a convergence going like this, something like that, that will be really bad, because then you have a model that didn't converge and it's not valid. So this right here is you guarantee that the method is working. And now this right here are the parameters that the method is estimating, sorry. And we have, each panel has two curves, one in green right here and one in gray. I always get this, and it's really interesting that it is still a belief among many researchers that you need to match the green line with the gray one. That's not true. You don't need to match them because the green one is telling you your prior knowledge of the phenomena. And your gray one is giving you the posterior knowledge. So if you match them, what you're saying is, I didn't learn anything. I didn't even need to go and take my data. I could have just drawn it by hand and I knew everything I needed to know to do that. So the fact that they're actually different is telling you that your data gave you new information. So don't worry if they don't match. Worry if there's something crazy. For example, one of them is, I don't know, for example, like this, that just all of it gets, all the mass gets in just one point. Then there might be a problem. Worry if your gray distribution tries to go, for example, right here, it's going all the way to 20. Maybe your corn requires bigger accumulation rates and it's not able to get all the way there because of your prior distribution. Then you worry, but don't worry that they're different. Okay. The first one will give you your accumulation rate. The second one will give you the memory parameters. These two are native of Bacon, so don't worry. Those ones are talk about the flexibility of your HTAP model. This line right here, this curve right here. And then this last two will give you information about your lead. This one will give you the information about your influx. If you see right here, this is really nice example because our influx that we put prior to this, we use the one that Appleby provided us with 50 becquerels per meter square per year. Plum says, no way, that's too small. And if you see a very thin line, green line right here, that's because Plum is saying the prior probability of me looking at these values was 0, but the data is telling me that it should be around here. So as I say, if you have information about it, that's great. You should put it in. If not, Plum usually don't worry much, doesn't hesitate too much to change it and to actually fix that using the data. And then again, the support activity, it was around 20. You see that the probability here was much better, but Plum is saying your support activity should be between 7 and 10. So it's refining, sorry. It's refining the information. Are there any questions up to this point?
Go ahead.
Somebody had a question?
I was just going to ask Marco what in the supported graph, it says S shape 5 and S mean 10.
This is the prior.
Oh, they're the priors. Okay. Yeah.
Yeah. So the prior was around 10 and the shape is about around 5.
Okay.
The just means that the gamma distribution looks something like this. If you change the shape, if you make it bigger, it would look more like this.
Mm-hmm.
If you keep making it bigger, it would look more like that. And if you make it smaller, it would look more like that. Right?
Yep.
So if you want your information to be closer, for example, to 0, you would actually change this value to be much more smaller.
Mm.
And that's the same for all the ones that use a gamma, which are this one, and this one. Right? And the mean just means where the mean is. In this case, will be somewhere there, somewhere around there, somewhere around there, somewhere around there. So that's just the mean of that distribution, of your prior distribution. Okay, so let's go to the main graph. Again, we're using years before present just because we wanted to keep it consistent with radiocarbon, and we just need to fix the dating somewhere. If not, it becomes a non-absolute dating method. And led to 10, it is an absolute method. So we needed to fix it into some sort of time scale. So we use before present. On this side, you will always see the scale of becquerels per kilogram. And that's because we graph your measurements of lead right here. These little squares are your actual measurement, your data. Let me see if I can now, oh, here you go. We finally decided to open, oh, I can see why. Here you go. I believe this is that data. So let's hope it opens. There you go. So it's saying 371.73, and that's around, that's exactly around 300 something, right? Yep. So these little squares are your data. Now, the little shadows are the actual simulations. So if one of your runs has its little squares, I don't know, right there, with all your shadows all the way somewhere else, and they don't match, you have a problem. Your run there was something wrong with that run, and you need to rerun it. Maybe play a little bit with your prior distributions, or maybe leave it longer, something like that. If you have this scenario right here, you can see that your data is all the way here, but your shadow is here. If that happens for all your data or most of your data, you have a problem. If you see this, for example, here, that it happens for one of two of the data points, I wouldn't worry unless you see something wrong with the HDOT model. Because what happens is the same as radiocarbon, we get outliers. Every method will eventually have some sort of outlier. This is a good example. It's coming out very nicely here, and then it decides to go up. Plum is saying something is wrong there. I'm gonna try to fix that. It fixes it, and then it continues. So I would call this to be an outlier, and the method is catching it, and it just continues to create a good chronology. If you see, there's nothing in particular there, and the chronology looks nice and smooth. So this is another way of verifying if your chronology or your method actually went okay, comparing those shadows with those squares. Okay, and well, this one will be.
Can I have a question on that graph?
Yeah.
Yeah. You have a very, like similar density of the data. Okay, the blue one. My question is why at the higher depth you have a large uncertainty in the model?
Oh, this is actually a good question. How do we make lead to 10 an absolute dating method? The only way to do that is to know exactly the day you went and took your core out of the environment, right? So, which is the coring date. So that's a very precise point. It's so precise that the uncertainty is almost none. So what happens is the method takes that into consideration, and it says, okay, so I have almost no uncertainty here. And as I go deeper, naturally, I'm losing that confidence. So even though my data has the same uncertainty, I have a point right here that it's telling my method, I'm exactly sure that I took that core that date. And Plum is saying, okay, you're so sure you took that core that day. I know that point comes from that date. then the uncertainty gets completely reduced. And we'll see that later when I show you cesium dates. That's going to happen again. You can see the model without the cesium to be quite big, and if you input the cesium and the lead agree, then it becomes much narrower. The uncertainty becomes much more narrow, because at that point you have a lot more information. So the method is taking all of that information into consideration.
Okay. Okay. Thanks. If I have more data in the lower part, can that uncertainty can be reduced or the same?
Do you mean lead to 10 data?
Yeah, lead to 10 data. For example, here, if you have more data in the lower part between, say, 24 to 30, you have more data of lead to 10. Can that uncertainty can be reduced or the same?
To be honest, I don't know. That's a good experiment. I think I'm going to try to do an experiment with that. I would say it will produce, but not enough to justify more examples taken from that part. Because it is more information, but at this part, for example, when you're at this area, you're so close to the support activity that it will be hard to actually make sense of it. You know what I mean?
Okay, yeah.
So it's actually a very good experiment. I never thought of making that experiment. But I can do something like that with simulations, that I just take more samples from that area. But I would say it will be reduced a little bit, but not enough to justify paying for more samples at that part.
Okay, thank you. I have that question later, when you connect it to radiocarbon. But okay, thanks a lot.
Yeah, perfect. We can talk about
Can I make a comment? It's our turn. So when you go down, the deeper samples usually have higher lead to 10 uncertainties. Would that would then affect the uncertainty of the age?
Yeah.
Would it?
Yeah. If you make these squares bigger, then the model don't know how to make these shadows more concentrated, and therefore it would reflect on a bigger uncertainty. This is a very good question. I'm going to show you some graphs later on that actually reflect what you're asking. Actually, let's go there now. I think it's, well, okay. rPlum is an R package, so let's get into that now. As I say, we can combine proxies for the support activity and lead to 10. You can combine it with radiocarbon, and then you get Gauss plots, which I'll show later on. We talked about this one already. This one. Let me first show you this. I won't get track of that. Just really quickly, I wanted to show this to you guys, because this will make a little bit more clear what's happening. Okay. My computer is a bit slow. Sorry about that. There you go. So this is actually, I created this simulation similar to what Martin did. The green line is the true chronology. I created that using simulations. This green dot right here is again the true supported and the true influx or supply of lead, and these are data points. Green dots are the true activity, and the dot with the line is the data I gave the method. So as you can see, Plum starts using a very stupid chronology and just decided to move everything. It's moving all the supported, all the supply, all the parameters until it finds somewhere that it makes sense. And you can see this right here. It's moving. If you look at this part, it's moving all the activities like crazy. It's trying to find something that matches the data and the the data and actually the true values. So this is actually what's happening behind the method, numerically speaking. We don't get to see this because then it will never end. This is just a couple thousand iterations. We have to run millions in order to get a good chronology. So just wanted to show you how it looks once it's actually running. There you go. But then we're gonna get here. Again, slow computer, there we go. Okay, let's use it like this because I don't know what's going on. Okay, what happens if you decided just to keep sampling like crazy, like just go, you have infinite number of samples that you can take, and there you go. So if you could take infinite number of samples, then you can go as deep as you want. This is a simulation I created to see what happens. If you see the data around 15 centimeters, we have rich background. Some people wouldn't even stop here around 10. But I decided to go all the way to 30, so twice as much after reaching background. And I create a simulation that has some cycles and then has a slope. So it's going up at a certain slope, but it's also doing some cycles. And I gave the method this simulation. And what happens is all the way to where there's good information is actually very, very good chronology. It follows the true, it captures the true, there is no problem. What happens after is it's actually capturing the true HDEP model that I created, but the uncertainties become way bigger. And something peculiar, the slope of this line is the slope of the simulation. So what happened is Plum learned from the data right here. And even though there's no more information in these samples, because this is basically support activity, there's really nothing there. It's using the information from all the previous samples to come up with a reasonable chronology. This is what we call the learning process. So it's learning from what happened before and try to apply that for some sort of prediction. Again, this is not magic. We're giving it all the information it needs. We're actually giving it all the data. Now, what happens if we don't give it all the data? What happens if instead of 30 samples out of 30, we only give him 15%, which is only 4 samples? Then we get something like that blue line. You won't be able to see that well, but it's right there. So it's actually not that bad, but it's not that good. What happens if we give him 15%? Then it becomes much better, but still it's not very good. But by looking at the lines, we don't really know if it's a good or bad chronology. The important part here is the uncertainty, if we are able to capture the true chronology or not. And for that, with 15%, the errors stay very good up to like 20, and then the uncertainties and the errors explode. That's normal with any method. But with 30%, look at that. Now, one of the things to look here is look at the uncertainty here to the uncertainty here. It becomes much bigger because the method is saying, I have way less data, so I need to be more careful. I need to be more conservative. And with 15%, the uncertainty becomes extreme. So if you don't have that much money for many samples, you will get a good chronology within the big uncertainties, right? But as you put more data in, you will get a much better result, a much narrower uncertainty. Now, how much is that? This is a very good example. I like it. It's a core from Mexico. Sanchez Cabeza and Carolina took it, and then we got a paper together using this sample. It's really nice. You can see Plum's uncertainties becoming so big here, and the CRS, which is this blue model, having uncertainties that are extremely small, right? But look at the data. We only have 1, 2, 3, 4, 5, 6, 7, 8 data points out of 30, which coincides with like 20% of the information. So having such a precise model doesn't really make sense when you have some little data available. How much is that? How can we check that? These are the results from a paper we're trying to publish right now. This is 3,000, almost 4,000 simulations, all of them coming with different percentage of information. We're giving it, for example, at 25%, I think we were giving it like 7 data points or something like that. And at 100%, we're giving all the data points to the methods. And then we have 2 CRS methods, what we call classical CRS and then revised CRS. This one is the one published by Sanchez Cabeza and Carolina, using Monte Carlo simulations, if you guys are familiar with that methodology. And these ones are the equations provided by Appleby, the raw equations with the uncertainty as Appleby show it. And you can see that the methods, in blue, you will see Plum. In green and red, you will see the CRS. You can see that the biases get better as you get more information for every method. But the biases or errors for Plum are smaller almost all the time. The interval length for the CRS methods is always small, always very small. It actually, with as more data you put in, it doesn't really change. You could actually get just 10% of the data and you will get the same, almost the same length of your uncertainties. But for Plum, it's just insane, going all the way to almost 60 years of length of the interval. On average, it could be much more bigger, but as you get more data in, you get that smaller. But this one is a nice one. Coverage means if you are able to capture your true chronology within those uncertainties. So what this is saying is, if you're under 2, which is the 2 standard deviations, you're capturing your true model on average within a 95% confidence interval. Now, this is very interesting because most people would only report 1 standard deviation. So this line right here. So you're almost guaranteeing that at some point, your H-step model, your CRS model, will not capture the truth, which is very worrying if you see these results, because you're saying we're publishing things that sometimes just don't capture the true values. Again, these are simulations, because it's the only way to see these sort of things.
Sorry, Marco.
Yes.
I think that's really interesting, very interesting exposition of the CRS model's limitations. There's just a question in the chat there from Andrea Johansson that says, by 100% of the data, are you saying you are using all the contiguous samples in the core?
Yes. Yeah. Basically, what we're saying, when you have 100% of the data, you're in this scenario where you're giving the method everything. So you continuously sample all the data and you measure all of them and you gave them to the to the method. Now, there will be a much beautiful sample like the question before, where you would sample some section twice. In the CRS or any other method, you would just take the mean of that or something like that. You will find some way of readjusting that. But in Plum, you can just put those two data points in and Plum will use them together. Then you will say you will be over 100% of the information, which is debatable, but we have to come up with some sort of language for that. So yeah, by 100%, you're using all the data. So this is a very good example of the limitations. And we always argue that the CRS is providing very small uncertainties. And people love that because then you're saying, oh, I'm very sure of my dating. But then you see this and yeah, you're very sure of that, but it's almost 100% sure that you're at some section of your core, you're not capturing the truth values. So it's just a word of warning when you're using the CRS, it's probably better to go a little bit conservative and increase a little bit of your uncertainties. It's a very good story here. When I was doing the PhD, I noticed those uncertainties being quite small. And before I came out with the idea of Plum, I actually artificially inflate them just to see what happened. And many of the problems that I was having with Bacon and the CRS merging together got fixed by artificially increasing that uncertainty. Because what I was basically saying to Bacon is like, yes, you have to be more conservative with these measurements, but with the radiocarbon, you don't need to be that conservative. I mean, it's a bit of a bit dodgy manipulation of the data, but I was just playing with the data. But just the fact that you can see these things and say, yes, the methodology is providing very small uncertainties, and just without knowing, I got it fixed by artificially increasing them. It was really interesting. I don't know if we should take a break. You mentioned, Simon, that you wanted to take a break at some point.
Yeah, well, why don't we? Maybe, how long do you think, Marco? 5 minutes or 10 minutes?
I'd say 10 minutes will be fine, I
10
guess.
minutes, okay. So yeah, if everyone could pop back here in 10 minutes and we'll continue along and yeah, we'll yeah. See you here back in 10 minutes.
Perfect.
Thanks very much, Marco.
You're welcome. See you in 10 minutes.
So Marco, there was a question about the last graph here, the coverage graph, about why the result at 50% for Plum was kind of tighter or closer together than at 100%. Is that just random chance?
I think so. I think it's random chance. One of the things that happened, these simulations, I'll show you. One of the things with these simulations is that they're not just one simulation. I'll explain this a bit further. Where is it? Simulation paper here. I'll try to look for that graph. So, oh, here. I don't know if you can see this, but what happened is we use these 3 different scenarios.
Yeah.
Where one that kind of looks like any old, nice looking led to 10 H-step model, core, whatever. One that is curvy, and the other one that actually has a decrease of accumulation on the deepest part, which is completely abnormal and completely strange. It's something that you don't really see happening. And actually, when you're at 25, the accumulation almost stopped here. So this is so that we believe that Plum didn't really knew how to deal with that. And that's here you can see that. when you have less data, that when you're looking at the dots, red is less data and this purple one is almost a complete core.
Ah, okay, yeah.
The reason is just for that core, after that section, it gets worse. It just, for some strange reason, more data makes it worse. And it's just that little, that simulation, but it just became so strange. And the thing, Plum doesn't really remove samples, just like the CRS method. So the CRS method did a lot better because it was removing all of that.
Okay,
It
yeah.
wasn't useful for the method, so it was just removed. So if you see that the same scenario for the CRS, you don't see dots, but it's because it wasn't able to capture them because it just removed them.
Yeah.
Plum tried to estimate them, and that's where it became worse. And I mean, probably to be fair to Plum, we could have removed that tail that didn't really work, but we felt that was cheating. It was like, no, it's actually better because it is the user who's actually looking at this.
Yeah.
And Plum is providing this methodology. So for that very strange core, it actually provides worse results. And I mean, the CRS just didn't provide results at all, but Plum did provide very bad results at that core. And I think that's why you see that, where is it? Here. I think that's what happened here.
Yeah, okay. So what, in that graph that you just showed, Marco, what was the y-axis, the normalized offset?
That's this same thing, Cobra.
Oh, it's the same thing. Okay.
Yeah, it is. We have to change the names. For the editor wanted us to change the names, so we did change the names.
Okay.
Yeah, it is the same. It is the coverage offset is the same. So as long as you're below 2, you're fine. As you can see, most of the cases does that. It was really strange. I mean, this is something that hasn't been published. It's interesting. For Plum, you can see, oh, what's going on there? You can see clearly the learning process. It's coming down and it's getting closer to 0, except for the case. But for the CRS, it's all over the place. You don't see a learning process.
Yeah.
It's really, it was really surprising. We worked with Sanchez Cabeza, Joan Sanchez Cabeza and Caro on this, the authors of that Monte Carlo methodology, and they were extremely shocked at these results. It was really fun to work on the paper. But
yeah, it makes me kind of think of all the lead 210 profiles I've worked with and see them in a different light now, I suppose.
Yeah. Well, as we always say, it's not about blinding using any method, not even Plum. You need to think about your core a little bit. Can I really use constant influx of lead? Can I use these accumulation rates? Can I use this? Can I use that? And that's why the lead to 10 community is always pushing at validate your chronology, because it is what you need to do. I mean, sometimes you cannot validate the assumptions, but sometimes you can just validate the chronology. With Plum, the system is different, but we have the same idea. We always pushing on double check your assumptions, double check that you're doing the things right, double check your numbers are correct. One of the things I always get from users is data points where the uncertainty is 0. So it's like, you're telling me you're 100% sure that your lead to 10 at this depth is this number. You have no doubt, complete no doubt about it. It's like, no, that's impossible. And people use these sort of things. And I told them, like, maybe your sheet is being, I don't know, round down or something like that, right? It's been rounded down or something, because it's impossible to have uncertainty of 0. And these sort of things are the things that just you need to think about sometimes.
Yeah.
Okay.
We've got about maybe 20 minutes left, I suppose, to leave some time for questions. So,
okay, sure.
Yep.
Does that sound okay?
Yeah, that's fine.
Yeah, there's only 10 slides left, so I'm sure I can finish them before that.
Great. Thank you.
Perfect. So these same graphs for the CFCS and the CIC, the other two most popular methods, as you can see, it's just craziness. We just don't go into much detail about these ones because it's the same and just the results are much worse. And this one is interesting. Instead of getting better chronologies, you get worse chronologies as you get more data, which was just an insane result. Now the learning process for Plum, as we saw up there, it just gets better as you get more data. You can see this is strategically missing data. So it is, for example, you take the measurement from 0 to 1, you don't measure 1 to 2, then you measure the next one and then not the next one, and then so on, so on. So in here, you're only using 50% of the data. As you can see, you get a very nice chronology and almost perfect alignment there. In this one, you're missing the background. Instead of reaching the 25, the 30, depth 30, you only reach 20. So you're missing a good portion of the background and you still get a very good chronology. I mean, not as good as that one, but you get a good chronology. And then if you're missing the top sediment, you get a much, you get, again, a good chronology, but the uncertainty at this area gets worse. It was this is the graph I wanted to show the person who asked the question about the uncertainty. It is also very good to know where to place your missing samples, because in here, the date that we have fixed here actually helps helps all the chronology along. But if you're missing that top part, then the uncertainty becomes big all the way, and it just becomes so tabular instead of just increasing naturally.
I had a question. How you know we missed the top part of the section?
What do you mean?
For example, if you collect the sample there and you assume that is 0 level, right? Yeah. But the thing is, for some reason, the top part have been missing and you don't know it. And my question is, how do you know, you missed the part of that top section?
That's more like a coring question. Like we're right here, we're assuming you didn't measure it. For example, you have
Okay.
You didn't measure the 5 top centimeters, for example, right?
Mm-hmm.
The question you're asking is much more fun, because if you don't know if you miss it or not, what do you do? We've been having discussions about making the method maybe working with a sort of uncertainty at where the top is, but then right now it's just a discussion among the developers of Plum. If it is actually worthwhile using these things, or actually letting it to the user kind of readjust it. Like if you guys go to a core and notice that you're missing, say, 1 centimeter of the top section, then you adjust that you put the data adjusted. Or should we actually include a function in the method that will actually, have some sort of uncertainty at the top? But right now we're not sure if it's worthwhile doing it, because for legs, sometimes you don't get that. At least I haven't heard that much, that question often. I heard a lot in oceans. I don't know if that's where you're coming from. But
okay,
yeah, right. Yeah.
Thank you.
So again, the mathematical construction we saw up there was just for lead. So we can just call that this likelihood of lead. And this is how easy you can input new data into Plum. There's a likelihood for the cesium. And that's it. You just multiply it, give it to the method, and then, there you go. This is another data. You can see lead to 10 coming here, and then you can see a cesium right there. I don't know if you see it right there. And you can see this is a perfect example for that question of the probability. You can see, even though there's uncertainty here, it's almost white. So the method is saying, yeah, I have my doubts going up, but I'm gonna be more sure here. So the uncertainty is not symmetrical at that point. So the method is actually saying, yeah, my lead is saying me I should be a little bit older, but this one is giving me so much more information, I'm gonna go there. So the difference between manually putting it in and what Plum does is that the lead to 10 might disagree a little bit. Or not, it could just perfectly align. But it's not the user's decision. It is actually the method who is saying, oh, yes, this makes sense, I'm gonna go there. Which is a big difference. And again, you can have even more data in cesium, lead, and you can just add your radiocarbon. If you add your radiocarbon, you're gonna get something like that. So you can see even it got the radiocarbon actually help even the whole chronology, not just in that section, but over here as well. You can see it's going way nicer into the lead, into the cesium, sorry. And it didn't have any problem. It was just measure, and you don't see that trumpet that we were mentioning, right? Which is one of the problems people were having when trying to put the CRS into Bacon, that they got some sort of thing like that, and then Bacon trying to really hard try to go back into the rate for the radiocarbons. That's the advantage of actually including all the models within the same method. Don't do double modeling, which is what essentially happened when you use any other dating method for the lead and then put it into Bacon.
So do you think, Marco, that that's the use of the CRS model is the reason that there are these mismatches between lead to 10 and radiocarbon quite often?
Could be one reason, but there's a lot more reasons. I mean, there's reservoir effect, there's hiatuses happening around that period. I mean, again, you need to use some sort of criteria, but at least one of the problems gets fixed.
Yeah,
right. You don't.
At least you know now whether it's just the modeling or whether it's potential reservoir effects or hiatuses or some other thing. Yeah.
Yeah, exactly.
That's really useful. Yeah.
Yeah. So reservoir effects. So this is not, we're not going to cover this on our practicals, but just to let you know this exists. Our version we're going to be using is the one that is official and all that, but I have my own, not private, it's actually public, but the version of Plum I use for testing new things, which I call rPlum. It's actually publicly available in my GitHub, so you guys can download it and do all of this. This is a core taken in China that I helped with modeling. You can see a cesium right here, and you won't see any radiocarbon dates because this has been corrected for reservoir effect. But if you see, here is a distribution of reservoir effect. This means that the method is choosing the reservoir effect. So I'm not telling it, oh, my reservoir effect is about 3,800 or something. No, no, no. I'm just giving it the data, and it is actually correcting for reservoir effect itself. I'm working on actually publishing these methodologies. I work with something like this with Larissa, and it's actually a very nice methodology for when you have reservoir effects and you have, to be honest, you do need some cesium and lead for this to work. You won't be able to do it if you only have the radiocarbon, because you do need something that is actually not affected by the reservoir effect. It could work if you have, I don't know, a a date here somewhere. That could work, but you do need some sort of date that helps it correct it. But you don't have to actually extrapolate and then decide your reservoir effect. You just put in the data and it will decide your reservoir effect, and even with a probability distribution. I will try to show you how to run this version of Plum if you guys have some interest in it. But again, this is done in Python. So it's not the version we're going to be using for our practicals tomorrow. This is the comparison. That core nicely had some laminations. Here's the cesium, and you can see that our method, even though it has a lot of uncertainty, did capture the laminations quite nicely. So we actually got a good model there. So it actually works. I mean, in the lead 210 part, we're missing a little bit. We're still capturing the uncertainties. So yeah, that is Plum. I don't know if you have some questions that I could answer. I'm here to
there's one in the chat from Michael Fletcher asking, can you use radiocarbon on macros versus bulk sediment?
I guess what I'm saying is, thanks, Marco, this has been really great. And I remember having a chat to you at INCRA about correcting radiocarbon with lead 210. And you ended up doing it with Kristen's, and that was really appreciated. Thank you. The question I have was, if you assume that a radiocarbon date on a macrofossil is real, and you have them on bulk sediment, which often suffer reservoir effects, can you use your program to calculate the reservoir between those two? Or does it require something non-radiocarbon? Does that make sense?
Conceptually, you can. Like, it makes sense. If you are sure it's not affected by reservoir effect, yes, you can. It's something I never thought of before, so it's not implemented program-wise. Do you know what I mean?
Yeah, yeah.
Now that you mention it, maybe I should have a way to actually tell it these radiocarbons are affected by reservoir effect and these ones are not, which is something I can probably program quite easily, but I need to sit down and program it in. So conceptually, yes, but as the program is now, no.
Yeah, cool. And only if you have time, but if over the next couple of ones of these, you could run us through an example with this, where you're correcting, for want of a better word, radiocarbon with lead 210, that would be amazing, because it's something really quite important, I think.
Yeah, I encounter it a lot with many research teams, and so that's why I wanted to bring it up. Again, you guys will need to learn a little bit of Python. If you guys are comfortable with that, I'm happy to teach you. It is quite an easy. I try to make it as friendly as possible, so it is there, and I'll try to have that implemented in the next couple of weeks. So maybe we can have it done the way you need it. If not, we can just exchange through email, and we can try to collaborate to do that later on.
Yeah, thanks. I have one more question. It probably doesn't really relate to this, but when you have radiocarbon dates that are pre-bomb, and you have, can these be plugged into Plum?
Yeah. Post-bomb.
Post-bomb. Sorry, yeah.
Post-bomb dating, it's not a problem. I mean, as long as you're using the right calibration curve, it works. There's
cool.
no problem. Yeah, as long as you tell it the program which post-bomb curve to use, there's no problem. The Python version is a bit harder, but actually, no, it is already implemented. Yeah, in both versions, the post-bomb is not a problem. Yeah,
so thank you very much, Marco.
Okay, can I have questions again? Okay, when you show the data between lead 210 and cesium, and for example, like you have the data for the Boss-bomb carbon-14, okay?
Mm-hmm.
For bacon, I know everything convert to day, But the thing is now you have the lead-210 in activity and cesium activity, a different kind of activity. And bomb carbon-14 or boss-bomb carbon-14 in age, how you combine them? That is my question.
Oh, how do you combine post-bomb? Oh, I don't know if you worked with bacon before. Let me see if I can.
Yeah, I worked for bacon before, but the bacon you just use that the lead-210 as the, you know, the absolute day or something like that. Yeah.
Yeah. Well,
Yeah.
well, this is something I was going to show tomorrow, but just really quickly to answer your question is, you can see. Can you guys see that folder?
Yeah.
This folder contains 2 files. One has the lead-210 data, which is right here. I don't know why it has these little things, but this is the lead-210 data, right?
Yeah.
And so this is the data as density, the lead-210 activity, the uncertainties, blah, blah, blah. But next to it, you have this other file. And I'm pretty sure if you work with Bacon before, you will know this format.
Yeah.
So you know that format, don't you?
Yeah.
So basically what you're gonna do here is take your Bacon files, remove all the lead, remove the surface, add it to the same folder, and that's how you're gonna create a chronology with both files together. So you can just use the same files you were using for Bacon.
Yeah, I understand what you say, but I just wonder, you know, actually how it's worked, because the thing is, you know, in terms of mathematically, because you have, did you build the lead-210 chronology first, and then you use the probability to combine with, you know, like boss-bomb or cesium? Is it right? Or
yeah, let me show you. Where did I left my code? There you go. Let me open the presentation again. Basically, remember when I show you that there is some mathematical thing that you would just add together, multiply together? Here you go, here. So you have your lead data here. This is the mathematical construction for the lead, right?
okay.
This is your construction for the cesium. Oh, sorry, this is your lead. This is your radiocarbon, and then your cesium, and you would just add another one here with post-bomb.
This one is the in term of day, right? Not activity. That one is based the property of day. Okay.
Yeah, the same as they. That's why you need the proper post-bomb calibration curve.
Okay, thank you. Yep. One thing you mentioned tomorrow, is it? We don't have tomorrow. We have next week, right?
Sorry, next week.
Okay.
Yeah, next week.
Thank you.
So I had questions about the coverage that you had before when you were showing the graphs. So I just kind of quick. By coverage, do you mean for those curves that you had? I'm guessing if I understood it right, it means sort of you have 3 lines, and I'm guessing one is the average, the middle one is average, and the other ones are sort of up and down a standard deviation. Is that what's happening with those 3 lines, or is?
Let me explain really quick. So you have, for example, this one is a bit more clear, right? Yeah. This upper and lower part are the confidence intervals for how much the length of the intervals are. I need to show you another graph in order to make that a bit more clear. So give me a second. Here. Here. Should be different. So this is the actual paper. So let me here. So this is sort of what we're doing with this thing. there's a true chronology, and there's the uncertainties of the CRS and Plum, right? So along the whole core, we measure how big the uncertainties were. So right here, you can see the uncertainties are over, even though they look smaller. The uncertainties for the CRS here are so small that they're not capturing the true values here. And it happens again here. What happens is I took all of these points and averaged them, right? And that's for one simulation. So along that core, I did that for one core, but we have to do that 5,000 times. So we removed this version of that, this from that version because it became too crowded. But if you can see points here, right? So this, each of these is the average of one of those simulations. So all of those points are 4,000 of them. So in order to make it a bit more visually appealing, we took the average of each simulation and then the average of all the simulations together for information percentage, we call it, for how many samples we gave the method, right? Does that make sense now?
Yeah, that makes sense. So, but for the normalized offset or the coverage, does that mean, like, do you mean how big that 95% or you know,
no,
sorry, 1 sigma coverage or whatever it is that
how big the length of the interval is this one, that middle one. That's
Sure.
why this one is years. So on average, that will be, for example, for very low percentages of information in Plum, you will be about 60 years of the length on average. As where to the CRS, you will be, I don't know, 20 years.
Okay. But
Okay.
yeah, what my question was for the coverage, yeah. For that coverage, normalized offset bit. Yeah.
The coverage becomes a bit trickier. So let me explain. What happens here is if you cut this thing, let's say you cut it here, right?
Yep.
What happens is you will have the CRS will be, maybe here is a better point. So your CRS method is here, right? And your true value is here, but the uncertainty is here to here.
Yeah.
So in order to have some sort of measurement, but not in years, but depending on how thick your sample is, we actually divided it by the length of the interval. This means that how many standard deviations you're away from the true value. Does that make sense?
So wait, how many standard deviations you have from the true value? Okay, so yeah, you normalized it and figured out how many standard deviations you are from the true value. But and so okay, and so you did that for different percentages, and each one of those points is like an average of your, again, an average of the whole, on the whole curve. Is that what you're doing?
Yeah, exactly.
Yeah.
So I measured these errors that are now normalized,
Yeah.
and then all of that is the mean. So
Yeah.
one of that is 1 point.
Right, now I get
and then,
what you're saying. Yeah.
Yeah. So it's just to try to make it the most visually appealing, because there's no way we can analyze 4,000.
No, yeah.
So that way, it just becomes.
Sorry, and it means, so it means, you know, it kind of means with, even with 100% there, you had what, like 3 standard deviations for on average for your points. Oh, yeah. Sorry, 2. So you're mostly 2 standard deviations above or below your curve. That's what you're saying, yeah.
Yep. Yeah, which is
cool.
If you think about it, if you're reporting your methods in a 2 standard deviation way, you're sort of okay. But if you report, then you are in big trouble.
Well, I mean, sort of okay. I mean, it's still pretty bad.
Yeah, exactly.
Thanks.
So I think we're kind of up to time now, Marco. Thanks everyone for your questions and participation. That's been fantastic to get an explanation of the limitations of the CRS model, which we all thought was wonderful. Yeah, the next session will be, Marco will be doing more examples and getting to use our own simulations using your data. There's one question in the chat about compiling data sets, but we won't actually cover that next week, will we? We'll be doing that in the third workshop where we use our own data. Is that correct?
Yeah, so next time we meet, what I'll do is actually go through the whole process myself on how to create these chronologies. I'll try to cover how to create the databases, where in your computer to put them, and how to call them from the R program. So the objective of that will be for the session after that is for having everyone, or even that same section, having everyone installing the software and just asking questions. Let's troubleshoot until everybody gets the computer running. And the last session will be to actually have you guys working on your own data or some data that we provide you in order for everyone to get some on-hand experience of the method and the package.
Yeah, thanks very much, Marco. That's terrific. Sorry, the link that I just posted in the chat doesn't work, so please use the one in your Eventbrite invitation.
No, I think that I will send to everyone. I have everyone's email.
Okay, yeah.
But I think there is a space there in the link. See how half it's hyperlinked.
I don't know why it's
half
done that.
not.
Hang on, I'll repost the one from the top. See if that works.
Yeah, that should work now.
So if you can't access that, please tell Larissa via email. Her email's there in the chat, and then she can add you manually to the registered people. Yeah.
The other thing that I was going to say is the Zoom link for next week is the same. So just use the same link. And yeah, and also as Simon was saying, we are going to practice next week. So don't be disheartened or discouraged by the amount of theory that you saw today. So next week will be the fun, I guess, Marco, isn't it?
Yeah, next week you guys will see the actual programming and the actual creating the database, where to put it, and actually coming up with the figures. So yeah, should be fun next week.
Okay, thanks very much. Yes, the same link today. Yeah, thanks very much, Marco, and we look forward to seeing you next week.
Thank you.
Thanks so much, Marco. Great work. Thank you.
Bye.